Okay, so let's continue this lecture number 2, right? Okay. Okay, so last time we study a lot of the definition, right, of the thing that we need to agree, all right, like the definition of the system, the boundary, the universe, like something like that, and thermodynamics entropy. And so I also mentioned about the zero law of thermodynamics, right? And so we learned that actually the temperature is the key, right, quantity for that zero or the thermal equilibrium, right? So today we're going to start to explore a little bit more about the temperature. Okay, these words normally. Okay. So I would like to make a note that normally people, okay, right, associate the concept of temperature with how hot or cold an object feel when they touch it. Okay, that is a big misconception. Then you have so I would like to make sure that we do agree the difference between this how hot and cold of the object when you touch it. This is not the same thing that we define the meaning of the temperature. Right. Okay, so like for example, so let me think about example. Okay, okay, but okay, let me okay let look at a simple situation. Okay, so if you stand okay, this is a tile floor and this is the carpet, okay, which is of course, you can say that this is U. Okay. Okay. Well, you can say that this might be the fall. You can feel a bit cold than this one, right? Okay, that is a thing. But I feel. Oops, sorry. Four is colder than carpet, right? But actually, type 4 and carpet, they are in thermal equilibrium. Okay, it means that they are in the same temperature. So actually they have the same same temperature. So the question is that what make you feel different between why the fall is colder than the carpet, the heat, you know? Can you answer that? Can you guess what is the key to make you feel different? I mean, is it going to be colder? Yeah, is it more? Yeah, which actually both of them are in the thermal equilibrium. What is the key? Heat diffusion. Mm-hmm. Yeah, yeah. The thing is that the thing is that transfer energy by mean of heat, which we are going to define again later at a higher rate. Than carpet does. Okay, so your skin actually, your skin measure the rate of energy transfer by heat larger than actual temperature. Okay, so that is the thing. Now, so we're going to look at deep into the definition of the temperature. Okay, I would say a convention, not convention, convenient definition of this temperature is that it is a measure of average translational kinetic energy okay, associated with the disorder microscopic motion. Well, this is something to do with statistical mechanics, which is we are going to explore on this point more later on in this course. But the point now is that the temperature is the quantity that actually emerge from something tiny, yeah, in your system, something like that. The like the collective, the effective thing that actually give rise to the this quantity, yeah, of atom and molecule. Okay. So if I would draw a picture, so if you have a gas, so example, this is cartoon. Okay, we're going to do cartoon thing here. So suppose you have a box actually contain a huge number of molecules. Okay. Then ideal monoatomic gas. So basically, so if you have a gas actually moving randomly in this okay. Suppose you have this, the length of the vector represent the difference of the velocity of each of the atom in this cube. And you have another box, so I prefer to use This is orange or red here. Anyway, I think yeah, I think it's oh here. Okay. So this again, the red represent again higher kinetic energy of each of the atom in this box. Okay, so again, non-avalanche that actually you have this T and this T. Okay, I call this T pump, which is actually greater than this one, because on the avalanche, the kinetic energy of this, the box on the right hand side is, this is slow moving atom. Lower temp. Okay, so it's on avalanche. Okay, this is fast moving atom on avalanche as well. So you get higher this thing, but I would like to emphasize again, we are not going to look into what really happened in this box now, but we know that actually on the avalanche, that actually you look at this in the microscopic level, you get a quantity that called temperature here. But actually this temperature is something that actually relates to the avalanche phenomenon of this moving molecule atom in this box. So going to deal to deep into the motion of this atom again when we study statistical mechanics. Okay. So, however, in more realistic situation, this is so I put here and here, right? We should actually, in more realistic, you have not this kind of monoatomic atom, so you get like a poly thing or more complex system. So however, there are other types of energy contributed to the system and so all of them together is called and internal energy. Okay, so now you have a new word here, the internal energy, which is actually, we normally use this symbol U, right? Right. So the definition from this perspective of the internal energy is every type of energy that actually exists in your system. Okay. So for example, like you look at polyatomic gas. Polyatomic gas. Okay. So you have a box again. What do I mean by have this polyatomic gas? Mean poly, but is you have like two atoms that actually couple together here. Right. You have a bunch of them spreading around in this box. Oh. นี่มันวิชาศิลปะวะเนี่ย Okay, so we have this bunch of polyatomic things, type of gas. So you know that actually how so of them. So you have for the translational kinetic energy. You have that, right? You have translational kinetic energy of each of the couple of atoms here, right? And you have also to include vibrational, right? Okay, because your atom along this can be vibrate, right? It can be straight, can be vibrate in this along this direction. Then that you have to include into your model, and also rotational. Energy, okay. What I mean is that, so this is like, suppose this is the center of mass, so you have this can be rotated, right? And it's kind of vibrate and so moving around and so rotate themselves around, and you, so this is all the all type of kinetic energy that you have, and you have to be taking into account in order to define the temperature, okay. But this system is still simple. We have more complicated system like a water. So you have a glass of water, or next example, you have a tank, okay? A tank of water. Supports. So the molecule is much more complicate something like this, right? You have this okay, you have this kind of molecule from of the water, right? But the thing is that there are also some kind of interaction on each of the molecule, right? So I would say that I would like to draw this kind of potential kind of interaction that you could have. So there will be this kind of thing on each to you're going to, oh shit, is that okay? Yeah, are you okay? So you're going to get like a very complex network of interaction, something like this. So this kind of thing, okay? This support, okay? This kind of interaction. So in this situation, you have all this. You have to put here, right? Again, and you plus yes potential energy into this system, which is actually from the interaction, right? Okay, and all of this together, we define internal energy of your system. Okay, hope you have a clear picture of this kind of definition of temperature, right? Okay. But to be careful, this part of the energy does not contribute to the temperature. Okay, only the kinetic part. Okay, so well, actually, you can look at other example like a solid object. You're going to have again these two types of kinetics, not two types of energies like a kinetic and potential one, but the potential energy is different in the solid material, right? So I would say that this is cartoon again. This is a cartoon thing. Okay. So system with the same temperature. So we can say that, suppose this is a portion of the kinetic energy, like this is for monoatomic gas. And this is a poly. So this is only, oh, Yeah. So what we need to take into account, sorry, that only the translational kinetic energy, right? That is a definition of the temperature there. It's a translational. Okay. And is all the same. If this system and this system, I mean, like this box of gas and this box of gas have the same temperature, it means that they're going to have the same translational kinetic energy on average. Okay? Okay? And so this and this is again like liquid, or like a system that I put there, water there. You have this potential, right? Energy part. This would be vibration plus rotation right here, and then again, this is again translation. Okay. So here, if this portion of the translational kinetic energy of these three different systems are the same, they are in the same temperature, that you see that actually internal energy of each of the system is not necessarily the same. Right. Yeah. So I would like to put a remark here. They have the same temperature, but not necessary to have the same internal energy. Okay, this is the point. Okay. So let me summarize. If the temperature of two objects is the same, then their average translational energy is the same. Okay. So next we're going to focus, of course, more, because now we have new words in this context. The first one, the internal energy. The second one is heat. So next we're going to look at the definition of these two. As I mentioned earlier, it's all the energy of a system that is associated with its microscopic component. Okay. When viewed from a reference frame at rest with respect to the center of mass of the system. Okay? So, what does it mean by the last bit here? When views from the reference frame at rest with respect to the center of mass of the system, very interesting, because this is something to do with the observer as well, right? Yes. Can you give me, or can you share the idea? What does it mean by this? Okay. This last sentence, make sure that any bulk kinetic energy of the system due to its motion to space is not included in the internal energy. Okay? Do you understand this sentence? Okay. I give you time to digest this little bit, and so I'm going to give you homework to work out, and then you will see more clearly what does it mean by this definition. Hopefully. Okay. Next, we're going to look at the definition of this one, heat. Okay. Heat is defined as a process of transferring energy across the boundary of a system because of a temperature different between the system and its surrounding. Okay. So normally we note this, so we can say that actually his is okay, we can say that actually energy in transfer, which is actually we note this by this symbol Q. Okay. As I mentioned, so if you have your system, this is your system, and your system is a bit, this is your system, you have TS, and then you have, oh shit, oh sorry, you have surrounding right here, which is, so we know that, no, it should be T, this is TH, and then this is 0, okay? to make sure that this is the energy difference. Okay, and then this is the boundary. So you know that actually heat will get out from the system to the surrounding, right? Okay, through the barrier system. Okay, and it's going to stop when the system and the surrounding reach the thermal equilibrium, right? Yeah. Okay. All right. So note, heat is not energy in hot substance. Okay? Do not confuse the heat with the energy that actually contain your system. That is the thing. So if you say that, oh, you have a cup of coffee, has this really high temperature, and you say that, oh, this cup of coffee contains a lot of heat, then that is wrong. You cannot say heat is not something that actually contained in the system, but heat is something that actually flow from one system to another system. Okay, then you have to be careful. It is not radiation. Okay, do you understand this? Heat is not radiation, because well, when in at the noon, when you walk in the pathway, you feel very hot. Yeah, because you say that, oh, because the floor radiate the heat out of it, so it's wrong again, right? It's not the heat that actually the radiation that delivered from the floor is the electromagnetic radiation. Okay. Heat is not okay. Warmth, yes, warmth. Open U A R M. Yes. Yep. You cannot say that, oh, today there is a lot of heat in the air. Then that is not correct. Yeah, but you can say that, oh, in the hot day, the air is very high. It's a very high temperature. Yeah, that is a thing. Okay. Okay, then that what I would like to make sure that you don't miss it. Okay. So unit of the heat, unit. So we going, normally we say you have the calorie, right? Which is actually 4.186 joule, right? Well, you know that how to joining, yep, you have a dictionary between these two units, right? But I'm not going to talk about it because I believe that you learned it from the very first class of the physics. And anyway, let's next talk about specific heat. Okay, have you? I believe that you learned about this before. Can you tell me what is the definition of the specific heat? Yeah.
Heat that made the matter that change the state.
Change the state. Okay.
Liquid to gas, something like
Right. It's yeah. Not that clearly. So the definition is that if the system consists of sample substance, okay, so we find that the quantity of energy required to rise the temperature of a given mass of a substance by the same amount vary from one substance to another. Okay, this is the definition of specific heat. The quantity of the energy required to rise the temperature, which is actually different substance. You require different amount of energy. If you want to raise the one step of temperature, then you might need to put different energy like the solid and the water. Yeah, that kind of thing. That is why it's called specific, right? Because different substance, you need to use different amount of energy to make to raise the temperature. Okay. So if we set a heat capacity, so normally we use this symbol capital C, right, as a heat capacity of a particular sample. It defined as the amount of energy needed to raise the temperature of that sample by 1 Celsius. This is the definition of heat capacity. So if energy is the Q, produce a change delta T in temperature of a substance of a sample. So what we have is that, so you're going to have this kind of ratio, right? So then what you have is that C delta T, which is, I believe that you encounter with this formula from your high school level, right? Okay. So the specific heat, so normally we know it is by this small c of a substance is the heat capacity per unit mass, right? Because you see from this definition, right, with given mass, right? So we can, so what you have here is this one. This is a specific heat. This is given mass. Okay. Okay. This is a matter of substance. So here is an highlight. So this specific heat is essentially a measure of how thermally insensitive a substance is to addition of energy. Okay, this is kind of the thing heat. You can say that actually the specific heat is a measure of the how insensitive or substance to the addition of the energy in terms of heat right here. I mean, the more C, what that means that if you have the more C, you need also a more heat, right, to give rise right to give rise the temperature difference with a given with a certain given mass here, right? So you might have, so in a different material, you might have different, this, this means that you have to put different Q to give rise exactly the same temperature with exactly the same. This, it varies from, as I mentioned, it varies from one substance to another substance. Yeah. Okay, is that clear for you? Okay. So what we have now, from this formula, so you have this delta Q. Yeah, which is actually, this is very, basic formula that actually you use in the high school, right? Yeah. This amount of energy give change on temperature, right? Delta T. All right, that is what we have here. Note that the substance remain the same, right? Here. That is thing. Next, we're going to look at another type of heat called latent heat, right? This is the specific heat. Next, we're going to look at latent heat. So in this situation, that actually when you put energy in your system is, remains the same, but the change is temperature. Right, that is the thing, right? Now, you can guess that in this situation should be different, should be the opposite one. When you put the energy, the temperature stay the same, but the change is the phase of the substance. Right, okay? The transfer of energy does not result in a change of temperature. Right. Here. But in the phase of substance called a phase transition, okay? Like at the beginning, so you have you have ice cube, okay, which is here, and later on melting to be a water, right? They are stay at this, right? Okay. In this process, so the heat of from surrounding will get into your ice cube, right, and make this process happen, right? The phase change, but the temperature is stay the same, right? That is very simple example in real life. Okay. But again, different substances have different rate of change, or require different amount of heat to put into to change from this phase to that one. Okay. So all the phase change involve a change in the system internal energy Okay. But not change in its temperature. Okay. This is, I would like to put this to make sure that you get this message. Okay. So keep in mind that what happened here, when you put the heat into your system, what change is the internal energy, but yeah, but your internal energy, what is the internal energy? The internal energy consists of the kinetic part, right? And the potential part, right here. So the heat or the energy that we put into the system or get out of the system going to affect on this part of your system, okay, but not on this part. I mean, translational kinetic energy, okay. Like you have, again, you have a tank of water. This is a very hot plate, okay, very hot plate, I mean, very hot plate. And so in this you have a water, right? So there is a molecule here. Okay. So when it's get to the boiling point at boiling point, you will get a bubble. Actually, out of it, and then you get boop 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 boop. Right, this kind of thing, right? Okay. What will happen here is that the heat will flow a lot from in this direction. Actually, the intersection the surface of the tank and the hot plates, right? In this direction, the heat flow. Okay. So what will happen here is the molecule of the water will break. Or water will be break. Right, yeah. That is the reason why you get a bubble. So you're going to get a molecule, a big one out of it, and small one out of it. something like that, right? Okay. Oxygen and hydrogen, right? That is the thing come out of this. So this this heat going to put a lot of energy on this molecule, make it more not in the stable mode somehow, I would say that. And if you put enough energy, you can make the breaking, you can make the bond or the molecule break, and you get a free gas out of this. Okay. Again, this is an example in real life, right? So, well, we can, it's nice because it can be explained by really simple physics here. But I have a question. Do you know why do we have a bubble here when you boil the water in this way? You start to get a bubble at the bottom. Oh, not from the side. Why is that? Do you know?
At the bottom, it has a temperature in the air, and
Yeah, indeed. Okay, good. Very good. All right, okay. So, we now define a latent heat for phase change. Okay. I use this capital L as this delta Q and the change of the mass, because you see that actually the mass of the water is not the same at this boiling point right here. Then so this is the change in mass of the higher phase material. Which is equal to the initial mass of the lower phase material. If the entire amount of sorry, can I continue here? Of the lower phase material undergo a phase change. Okay, so you can see that what I mean by the higher phase and the lower phase here, this should be the lower phase here because the direction of the change in this way, this is the higher phase. Okay, yeah. In this situation, it means that so if the total the ice cube here melt completely to this water, the delta M is nothing but the mass of the ice cube or the water. That's the thing. Undergoes there goes a fair change. So I'm sorry, my handwriting start. It gets worse somehow. Okay, so now we have latent heat of fusion, which is labeled by this symbol. Which is used for solid to liquid. Right. Next one, latent heat of vaporization, which is this one, is used in terms of liquid to gas. Okay. I'm going to give you example in homework to work out on this precisely later. All right. Now we learn more thing. I mean, we learn more definition of quantity that we're going to use in this context. I mean in thermodynamics. Today we start again with the definition of the temperature. But in the previous class, we more or less define it in terms of math somehow, right? To be a condition to state the zero law, right? But today we define temperature again in terms of the kinetic energy, the translational kinetic energy, and we learn what is the internal energy and what is the heat, right? And this kind of thing. Next, so we're going to look at the definition of the work and heat process. So now we look at work and heat in thermodynamic process. Well, actually, we learned already what is the definition of the heat, right? But we need to look at the definition of the work here. So in this context, I mean in thermodynamics, we describe the state of a system by using state variable, which is actually we defined in the previous class, right? Like this PVT, right? Yeah. And as well as the internal energy as well, right? So we have, so in fact, we have another set of variable call share call transfer variable and which can be negative and positive depending on whether energy is entering or leaving the system. Okay? Positive. Positive. Depending. Sorry. Depending. Is it better? No, maybe not. Okay. And so if you look at this definition of the transfer variables, of course, heat is one of them. Heat is one of transfer variable, right? So you can say that when heat getting in your system, and then this is surrounding, you can say that, oh, you can say this, you get a plus sign, but in the case that actually your heat is getting out, you may say that is a minus sign. Okay? It depends on the direction of the energy entering or leaving the system, then yeah, it definitely one of these transfer variables. And it's not a state variable, right? It is not state variable. Keep in mind that then. Okay. Next, we're going to look at a next quantity that's called work. Okay. Work. Okay. For simplicity, right, we're going to look at a completion of gas. Okay? So suppose that you have a tube, okay, and you have a piston on top here, compression. Okay. And you have a molecule of gas in this cylinder too. Okay. And this has the area A, the piston. And at this state, the pressure P, and you have the volume V, right? So next, when you push this piston further down, okay, you exert the force to this piston, and it's going down, and so this bunch of molecule, a gas molecule, will be compressed, right? Okay, by distance dy, let's say. So let's say that actually this is the state 1 and this is the state 2. Okay. At 1, so the system is in equilibrium. I mean, so you it is stay still, and the gas has a pressure P and the volume V right here. So the magnitude of the force, right, exert by gas, by a gas on the piston is this one. And so the magnitude of the force exerted by the piston on gas is this one as well. So that is a reason why this is in equilibrium, right? Because so you have a force acting on here and also another force acting on here, which is actually the same amount. That's why the piston stays still, right? And this is nothing but the Newton's third law, right? Yeah. In second one, the piston is pushed invert, right? The gas is compressed, of course. Quasi-static. What I mean by this quasi-static is slowly enough to allow the system to remain essentially in internal thermal equilibrium at all time. This is the definition of quasi-static. It means that you push this piston, but in a very slow, right? To make sure that your system is still in the equilibrium. So now we have a work done on gas, on the gas is defined by this. So you have here, suppose that you could, this is J, this is I, that is the thing. So you're going to get this one, which is PA dy, which is dV, right? So this symbol represents D, this is the infinite, decimal chain. Okay. All right. And I also put a bar here to make sure that this bar indicate the nature of the work. I mean, which the nature is mean that the nature is a transfer. These are transfer variables, right? Okay. So if a gas is complex, so your dV is negative, right? It means that, so this one is greater than 0, right? And if a gas expand. Your dv is positive, and this one is less than 0. Okay. So if you want to compute a total work, right? So you need to do the integration from the initial volume to the final one, right? Of this dW here, which is actually okay, this one. All right. In order to compute this integration, you need to know how this P depends on the V, right? You need to know okay, P and V, the relation between these two. What time is it now? Can I take 5-minute break? โอ้เหนื่อยใช่ไหมโอ้ ลืมไปว่าอัดวิดีโออยู่เขาเป็นแค่ที่แต่ว่าปล่อยไว้ไลฟ์อย่างนี้ก็ได้ครับเหนื่อยเหนื่อย Okay, so let's continue. Oops, ใช้พลังงานเยอะไปหน่อย So let's continue here. Okay. So you can see that in general, this P is not necessary to be a constant during the process. So what you get, you may familiar with this PV diagram, right? So you may have this part. Okay. So the work done during the process is nothing but the area, right? And the curve work done during the process. Okay. And so there is some very interesting feature. So if we say that actually this is initial point and this is the final point. So this is not the only way that we can go. And you say that, so you can go along this way first and go up. Right here. So the area and then the curve will be this. Right. I would use this white chalk. And then this new part, we have this yellow W, which is not the same with this one. Yeah, of course, because it's quite obvious because you get different area under the curve, right? And you can go up here first, and then you go here. Right. If you do this, so you're going to have this area under the curve, which is, I shall call it the blue one, which is, of course, greater than W, which is. So from this feature, we see that work is a quantity which depend on part from I to F, right? Yeah, you see that? Okay, hope you. And then, well, and again, this is very interesting point because last time, I mean, in the last lecture, we study a quantity that actually possess kind of part independent feature, right? But this is not the one. Yeah. Yeah, this is part dependent. Yeah. Part dependent. Okay. Then you cannot use, yeah, that is the reason why you cannot use this quantity as a set quantity variable, but it's the, yeah, it's a transfer variable. Oh, yeah. Where is my note? Oh, here, okay. Okay, so let me say a little bit more about reversible. Yeah. You know what does it mean by this? What is a reversible process? Yeah, sure. Of course, you can use the board. Yeah, then I can sit here.
When you use the chemical symbols, this is the process. When the process is a reversible process, you can write it here. So the reversible process is if we have a system A, the initial state and the final state. So in between A and B, we can change the state from A to B, and we can change back from B to A. So this is a reversible process.
Okay, yeah.
Something like that.
Right, okay, very interesting. Yes, yeah. It's but that is a kind of nice example that you put there. But in this context, we have to be careful to define what what really happened here. So let's see. So the reversible process is a one that, yeah, of course, can be reversed, right? Can be reversed by means of infinitesimal chain in some property of the system without loss or dissipation of energy and can be reversed without, again, causing change in the surrounding. That is the key thing here. Not only your system can be reversed to be the same, your surrounding has to be get back to be the same as well. That is the definition of this reversible process in this context. Okay. Then next is a reversible process. You can guess what is the irreversible process, right? Irreversible process is the one that is not reversible. Right. Very simple. Okay.
Oh.
Right. For example, you have a cylinder chamber of gas, and you have a very thin membrane here, and you have a gas molecule here, right? Later on, this gas will get through this membrane and expand to fill out completely this chamber, right? And if you want to push this gas back to this portion, you have to use a piston, to use the force, right, to push it back, right. This process is irreversible because there is a permanent change in the surrounding, because the surrounding you use the force, then that is caused the change of the surrounding. That is the thing. Okay, this is not irreversible in this sense, but actually most of the process in real life is irreversible. Reversible is, I don't know, I might try to think about example of a reversible process in real life. Do we have that? No, because interesting.
Irreversible.
Yeah, reversible process in real life.
Reversible process.
Yeah. Do you have that example?
Ice making.
What?
Ice making.
Ice making. How could that be a reversible process? I mean, you mean from the water to the ice?
Yeah.
But it's called the change of the surrounding, right? Because you use the energy.
Yeah. Okay.
That is not the word reversible. That in this, yeah, this is the definition. You have to remember this part. Otherwise, then this is like the definition of the third law of the Newton, right? You have to remember not only that actually the force had to be the same magnitude, but had to be exerted on different objects. That is the definition of the third law. But most of the people forget about exert on different objects. You have to, yeah, like this one, you have to keep actually without causing change the surrounding as well. Otherwise, you cannot say that is reversible. Us is a very good example of a reversible process, because every second you aging, right?
Yeah.
And you cannot get back a second before, right? You get go on keeping forward into the future, right? And aging in very second. Yeah, that is the thing. All right, so let me go on a bit. So, it's very difficult. I think I could not think about example in real life now. I think that I will find that in the internet. And the next time I'm going to mention about it. But we could demonstrate somehow. We could somehow define a kind of reversible process in this context in this way. So example, reversible process, okay. So you have let's put in this way. This is a piston. Okay, and you have a molecule which is actually Vi. Okay, this is the initial state. Okay, and what we are going to do is that very interesting. What we are going to do is what we can do is I am going to put a tiny mass. I call this delta M infinitesimal mass. Okay, put in it. It means that this piston will get down a bit, right? Yeah, it get down a bit. But this process is still in thermal equilibrium. Okay, it means that so what you can do is that you can add more. You can add more mass, another bit of mass, right here. And then this piston will get down furthermore a bit, and then it's still in the thermal equilibrium. Yeah. And once you continue by doing this, I don't know, because this might take you an age to finish this process. You know what I mean by the age, right? Yes. It might take you a very, very long time to finally you might successfully to push the piston low to this down to this point. So it means that so you get this infinite tiny number of masses here, right? Yeah. Yeah. This is a bunch of, okay, and then this will be in final state. And so what you can do is that from this one, oops, sorry. หิวข้าวแล้ว หิวข้าวไหมครับเนี่ยครับ So you can take out one delta M at the time, right? And this going to step up a bit, right? Here. And then, of course, you continue to take out one at a time, right? And then at the end, you will get back to this state. This is kind of reversible one. Yeah, because we can say that there is no heat exchange between the system and the surrounding in this context, right? No heat exchange between the system and surrounding. So we can call this, it might be an adiabatic, right? Yeah, adiabatic process, okay? So, yeah. So, it means that if you look at the PV diagram, so suppose this is the initial point, and this is the final point, right? So you have a curve that actually can go up and go, it's go up and go down, exactly the same path here, all right? And then this this dash line give us a different temperature, right? Because the different PV give us different temperature. Yeah, we're going to discuss about this property of it next time. Okay, so this is the way that we can ideally create reversible process. Okay, and we're going to use this to construct the heat engine. To consider the heat engine next class. Okay. So let me see that whether I would like to continue or stop here. Well, I'm so tired now. Let's see. Because I really need to finish the first law. Okay, let's continue a bit. Okay, so let's continue a bit. So now, isolated system, which is actually, I mentioned to this definition of the isolated system before, right? So there is no change of the heat, right? And no change, nothing change at all. So so it means that if there is no heat add up or taking out of the system, it means that your internal energy will be the same, right? Then this is a consequence of this one. All right. Then this is, you have to remember, for the isolated system, there is no change. Yes, that is the key. Okay. Next one. Cyclic process. Cyclic process that this, okay, it can this, and then you call this is called cyclic, right? A and B. Okay. So since your system is get back to the initial point, so again there is no change, but there might be that the way that you, yeah, that add up.
It's not.
Right. Should actually this one, right? And this would be the total amount of work, right? That we require during the cyclic process. Okay, you know this symbol, right? Okay. Yep. So the amount of work required to change an isolated system from state I to state F is independent of how work is performed. Okay, independent. Okay,
From state. From state.
that I to the F.
This in this is what?
Independent. Sorry. Independent. Okay. But okay, this statement, this whole statement here, indicate that there is another function of state of the system, which is actually U, the internal energy, which is the function of P and V. Which is okay. So it means that the change of this U going to be exactly the same amount of work that we put into the system. However, system that are not isolated the chain of energy is not equal to amount of work done. So it means that there is another way that the internal energy of your system can be changed, like if you have attached these two systems which have different temperature, so the heat will flow from the higher one to the lower one, right? And making this internal energy of this one change, right? So in total, the chain of internal energy is going to be this part put together. And yeah, that. So the meaning of this, and then this is the equation, I would say star. And so if you recognize this equation, it's nothing but something to do with the first law right here. So the star means that a given change in internal energy infinite variety of pathways or or the possible combination of Q and W that add up to a given system given of theta. Okay, this is somehow the first law, I would say. This is the first law. So it means, so from this statement is not directly, it does not implies the conservation of energy. Okay, that most people misunderstood about this, because when we say about the first law, they say, oh, this third law is nothing but the conservation of energy. Of course it is, because everything that you put into a system going to change the internal energy. The energy can be changed, the form, but the definition is to define this internal energy. This internal energy can be changed by the effect of Q and W in infinite different ways. That is the key idea of the first law. And the conservation of the energy is thing that follow later. The conservation of energy is not the definition of the first law. The first law is what I did explain earlier. You get that?
Okay.
So it means, let me give you example a bit. Like, example, if you have a tank of water with temperature T, and if you want to increase the temperature of water, you can put it on the hot plate, right? Very hot plate, and then or you have, if you can stir it. I mean, you can mechanical rotate this machine to stir the water until its temperature is increased exactly the same with this one. But you see that the process is different. I mean, in a way that we increase the temperature with delta T. But when your system reaches this T plus delta T, you cannot trace back which technique that you use to add up this delta T. This is the way, this is the property that we mentioned last time, right?
Yes.
There is the history of the process is relevant. Okay. So there is no statistical test by which you could determine with which way of boiling or stirring, heating up, or combination of it. Okay, you can put it on a hot plate and then you can stir it. This is the combination, and then you cannot say when it reaches this stage, you cannot say which which kind of technique that you use to increase the temperature. This is the one that actually you put the heat, right? And then you put the work, and you can combine it, and then you can make the internal energy change, right? But there is no way you can say which technique that you use. I mean, if you do it privately in your room, and you ask me which way that you did to increase the temperature, I cannot tell. That is the thing. Okay, so I'm going to stop here for today. This is we finished kind of the first law. Next time we're going to look on the second law. And so, yeah, that's it. I hope you get my point. Okay. Then that's it. Thank you.